In order to understand more periodic properties, we need to discuss the effective nuclear charge, otherwise known as Z effective. This is the pull felt by an outer electron from the nucleus. Now, Z effective is calculated as Z, the atomic number, minus the shielding constant. The shielding constant can be approximated as the number of inner or core electrons. And you can see that as Z effective increases, radius decreases. We will use Z effective to explain many periodic properties. There is a periodic trend to the effective nuclear charge. In general, as you go across from left to right, Z effective increases. This is because the number of protons increases while the number of core electrons stays the same. As you go down a family, Z effective decreases. This is because you start adding core electrons with an increasing number of n. In order to understand the size of atoms, we have to understand how we measure atomic radius. This depends upon the type of element. Metals exist as crystals, and we can measure the atom's radius as half the distance of the crystal lattice structure. Whereas molecules, or atoms that exist as a molecule, we measure the smooshed together distance, the covalent radius. This is half the bond distance. These values are measured values and are subject to experimental error. So we can see that as we travel from left to right, atomic radius decreases. And as we travel from top to bottom, the atomic radius increases. How does this compare with the Z effective of each of these atoms? If we graph atomic radius versus the atomic number, we can see a general trend in the radius. This is what was developed on the last slide. However, we can see there are some anomalies in the trends. This is due primarily to the differences between how the radii are measured. So let's examine a real problem. If we refer to a periodic table, arrange the following atoms in order of increasing atomic radius from phosphorus, silicon, and nitrogen. So from examining a periodic table, we see that nitrogen and phosphorus are in the same group, 5A. Now, since we know that as we go down the periodic table, radius increases, so phosphorus must be bigger than nitrogen. Now, silicon and phosphorus are members of the period 3, and we know that as we go across from left to right, the atomic radius decreases. And since phosphorus is to the right of silicon, it must be smaller than the silicon. Therefore, in order of increasing atomic radius, nitrogen is smaller than phosphorus, which is smaller than silicon. In general, to solve this type of problem, we need to examine the relative positions of each element on the periodic table with respect to each other. Then we apply our periodic trends. So how does the radius change when we go from an atom to an ion? As we can see with our cations, the atomic radius of lithium is about 150 picometers, but the cation is slightly over 50 picometers. So we can see that as we become cations, atomic radius decreases. Now, similarly, as we become anions, the atomic radius will increase. As we can see, the cation is always going to be smaller than the atom from which it was formed. This is because as we remove an outer valence electron, the Z effective actually increases. Whereas when we add an electron to an atom, that anion is always going to be larger. That is because As we add an electron, we increase electron-electron repulsions, thereby making the ion larger. We can see some representative radii on the table. Now, notice that if the cation forms more than one stable ion, the higher oxidation state results in a smaller ionic radius. For example, iron 2 versus iron 3, or copper 1 versus copper 2. Let's apply this knowledge to a question. Indicate which of the following is bigger: the nitride ion or the fluoride ion, the magnesium cation or the calcium cation, and the iron 2+ or the iron 3+ cation. To solve this problem, let's look at the positions, charges, and electron configurations of each atom or ion in each pair. For the first pair, these are isoelectronic. However, nitrogen having a larger 3- charge results in the ion being much larger than the fluoride ion. For the second, calcium is lower on the table than magnesium, so it starts off with a bigger atom, therefore the calcium ion is going to be bigger than the magnesium ion. For the third, the electron configurations show one more electron in the Fe2+ than the Fe3+. This results in a larger Fe2+ ion.